like a detective following a trail of clues, because that is what this is, a mystery, and the suspect is nothing itself. Start with something you already know, even if you do not realize you know it. You cannot pin a thing down perfectly. That is not philosophy. That is not hand-waving. That is a law as firm as gravity. Werner Heisenberg figured this out in 1927. He showed that there is a fundamental limit to how precisely you can know two related properties of anything at the same time. You want to know exactly where a particle is, fine, but then you cannot know exactly how fast it is moving. You want to nail down its momentum with perfect precision? Good luck, its position becomes a blur. And this is not some trivial smearing out. This is not about measurement being hard. I want you to really feel this, because it is the key to everything that follows. Imagine you have a friend and you ask them, where are you right now? They say, I am standing on the corner of 5th Avenue and 42nd Street. Great. Very precise. But now you ask, and how fast are you walking? And they say, I have absolutely no idea. I might be standing still. I might be running. I genuinely do not know. That sounds crazy for a person on a street corner. But for an electron, that is exactly how nature works. The more confidently you can say where it is, the less you can say about how it is moving, and vice versa. The universe keeps a ledger, and the product of those two uncertainties can never drop below a certain minimum value set by Planck's constant. That is the tax you pay for existing at the quantum scale. All right, so what does that have to do with nothing? Well, think about what nothing means if you take it literally. No energy, no motion, no vibration, complete total stillness, zero everything. But Heisenberg just told us that complete stillness is illegal. If something has exactly zero energy and exactly zero motion, then you know both its position and its momentum with perfect certainty. Both are zero, and that violates the rule. Nature will not allow it. This is not a technicality, this is fundamental. The universe is physically incapable of producing a state of perfect rest. It would be like asking a river to flow at exactly zero speed and simultaneously be at a perfectly defined location. Quantum mechanics says no, something must be moving. Some residual tremor must exist. So what does nature do instead? It fidgets. Even in the emptiest, coldest, most desolate patch of space you can imagine, there is a tiny, irreducible jitter, a trembling that can never be turned off, no matter how hard you try, no matter how clever your technology, no matter how patient you are. Physicists call this the zero-point energy. It is the energy of nothing, the lowest possible energy a system can ever have, and it is not zero. Let me give you a picture. Imagine a ball sitting at the bottom of a bowl. In classical physics, the old-fashioned pre-quantum physics, that ball can sit perfectly still at the very bottom. Zero energy, done, dead still. But in quantum mechanics, the ball cannot sit still. It wobbles, it oscillates, not because anything pushed it, not because there is any heat left. It wobbles because sitting perfectly still is not an option in this universe. There is a minimum jiggle built into the system, and you cannot get below it. You cool it, you isolate it, you remove every possible disturbance, and it still jiggles. That minimum energy is 1/2 times the product of Planck's constant and the natural frequency of the oscillator. 1/2 H bar omega. Remember that formula. It will haunt us later. Now that is one ball in one ball. One little oscillator. Barely worth worrying about. The energy involved is inconceivably small. For a single quantum oscillator vibrating at the frequency of visible light, the zero-point energy is around 10 to the minus 19th joules. That is nothing. Less than the energy it takes to nudge a single molecule of air. Who cares? Well, it depends on how many bowls there are. And this is where the floor drops out. Because the universe is not one bowl, not two bowls, not a million bowls. The universe is full of fields. Not just one field, but many. And each field fills all of space. Continuously. Everywhere. Without gaps. Without interruption. Now, what do I mean by a field? I mean something very specific. That a field is a quantity that has a value at every point in space and time. Temperature is a field. At every location in this room there is a temperature. The air pressure is a field. At every point in the atmosphere there is a pressure. But these are classical fields made of molecules. The fields I am talking about are fundamental, They exist even in a perfect vacuum. They are not made of anything smaller. The electromagnetic field, for one, it fills all of space. Every point in that field, at every possible frequency, at every possible direction of vibration, behaves like its own little oscillator, its own little ball with a quantum ball jiggling at the bottom. And every single one of those oscillators has this minimum jiggle, this irreducible zero-point energy. How many of these oscillators are there? Think about it. The electromagnetic field exists at every point in space, and at each point there is not one oscillator but infinitely many, one for each possible frequency of vibration, low frequency, high frequency, and everything in between. Radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, gamma rays, and beyond, up to whatever the highest frequency in nature turns out to be. You see the problem, there is no obvious ceiling. At every point and at every possible frequency, you have another oscillator contributing its little bit of zero-point energy, its 1/2 h bar omega. And since omega, the frequency, can go as high as you like, and there are infinitely many points in space, you start adding them up and the sum does not converge to a nice number. It does not converge at all. It goes to infinity. Infinity. In every cubic centimeter of empty space. Now hold on. That sounds absurd. An infinite amount of energy sitting in every tiny volume of vacuum? That cannot be right. And you are correct to be suspicious. Physicists were suspicious too. In fact, for decades the standard response was, ignore it. Subtract it off. It is just a constant background. It is the same everywhere. It does not do anything. Physics only cares about energy differences, not absolute values. So set the vacuum energy to zero by convention and move on with your life. And here is the remarkable thing. For almost everything we do in quantum electrodynamics, that strategy works brilliantly. You subtract off the infinite vacuum energy, set it to zero by decree, and compute everything else relative to that baseline. The answers you get for real, measurable things, like how an electron scatters a photon, like the precise magnetic strength of an electron, like the shift of spectral lines in hydrogen, those answers match experiments to breathtaking precision. Let me give you a sense of how precise. The magnetic moment of the electron, this is a number that tells you how strongly an electron responds to a magnetic field. We calculated this number using quantum electrodynamics, summing up contributions from Feynman diagrams involving virtual photons and virtual electron-positron pairs buzzing around in the vacuum. The calculation required evaluating hundreds of diagrams, some involving 4 or 5 levels of these virtual corrections. And when we were done, we had a number, and experimentalists went into their labs with their exquisite equipment and measured the same number, and the two agreed to better than 1 part in a trillion. 1 part in a trillion, that is like predicting the distance from the Earth to the Moon and getting it right to within the thickness of a single sheet of paper. So the theory works magnificently, spectacularly. No theory in the history of science has ever matched experiment this closely. And yet, there is this infinity lurking in the basement. This infinite energy of nothing that we chose to ignore. We shoved it aside because it was inconvenient, because we did not know what to do with it, because subtracting it seemed harmless. But is it harmless? Let me introduce you to a Dutch physicist named Hendrik Casimir. In 1948, Casimir was working at the Philips Research Laboratories in Eindhoven, studying the behavior of colloidal solutions. Not exactly the bleeding edge of quantum physics, but he started thinking about the forces between neutral particles, and that led him to a conversation with Niels Bohr, and Bohr said something that changed everything. Bohr suggested the forces might have something to do with zero-point energy. Casimir followed the thread. He asked a very simple question. What if you take 2 metal plates, perfectly flat, perfectly conducting, uncharged, and hold them very close together in a vacuum? Classically, nothing should happen. There is no charge. There is no current. There is no reason for a force. The plates should just sit there, inert, bored, doing absolutely nothing. But Casimir realized something subtle. Those zero-point fluctuations of the electromagnetic field, the jiggling of nothing that I just told you about, they exist between the plates and outside the plates. Outside the plates, every possible wavelength of fluctuation can exist, every frequency, every mode. The field can vibrate however it likes. But between the plates, only certain wavelengths fit. Think of it like a guitar string. A guitar string fixed at both ends can only vibrate at frequencies where whole numbers of half wavelengths fit between the pegs. You get the fundamental, the first harmonic, the second harmonic, and so on. You do not get every possible wavelength. The boundary conditions restrict what is allowed. The metal plates do the same thing to the electromagnetic field. Between the plates, only those vacuum fluctuations whose wavelengths fit neatly between the two surfaces, whole numbers of half wavelengths, can survive. All the other modes are suppressed, so there are fewer fluctuations between the plates than outside them, fewer modes, less vacuum energy density in the gap than in the surrounding space, and that difference in energy means there is a force, a genuine physical force pushing the plates together. Think of it like the pressure difference that holds a suction cup to a window. Except this pressure comes not from air but from the quantum vacuum itself. There is more nothing pushing on the outside of the plates than on the inside. So the plates get squeezed together. Casimir calculated this force. The formula is beautifully simple. It depends on Planck's constant, the speed of light, the area of the plates, and the inverse of the fourth power of the distance between them. Nothing else, no material properties, no charges, no coupling constants of any kind. Just the geometry of empty space and the fundamental constants of quantum mechanics and relativity. For decades, this was a theoretical prediction, a curiosity, a parlor trick of quantum field theory. The force is extraordinarily small. For two plates, a square centimeter in area, separated by about 1 micrometer, 1/1,000,000th of a meter, the force is roughly 1/10,000,000,000th of a newton. That is about the weight of a single red blood cell on the surface of the Earth. Tiny, absurdly tiny, but tiny does not mean zero. The first person to try measuring it was Marcus Sparnay, also at Philips in Eindhoven in 1958. He tried, his results were, shall we say, not conclusive. He could not rule out the force being zero. The best he could say was that his measurements did not contradict Casimir's prediction. That is a physicist's way of saying, I tried, but the signal was too small and my equipment was too crude. For nearly 40 years after that, the Casimir effect remained largely a theoretical result. People believed it, the math was clean, but nobody could pin it down experimentally with real confidence. Then, in 1997, Steve Lamoureux at the University of Washington built an experiment that changed everything. Instead of trying to align two perfectly parallel plates, which requires absurd precision, better than 100,000th of a radian over a centimeter, he used a gold-coated sphere and a flat plate. The sphere plate geometry sidesteps the alignment problem entirely. He mounted this apparatus on an exquisitely sensitive torsion pendulum, a horizontal bar suspended by a thin tungsten wire, and placed it inside a vacuum chamber. When the sphere was brought within a few micrometers of the plate, the pendulum twisted. Something was pulling the two surfaces together. No charge, no current, no classical explanation. And the magnitude of that pull agreed with Casimir's prediction to within 5%. Let that sit for a moment. A prediction made in 1948, based entirely on the quantum fluctuations of empty space, confirmed nearly 50 years later by direct measurement. The vacuum pushed two objects together. Nothing has muscles. So the zero-point energy is not just a bookkeeping trick. Well, it is not just a mathematical convenience we can subtract away and forget about. It has physical, measurable, laboratory-confirmed consequences. The vacuum is not empty. It has structure. It exerts forces. It is a thing. And once you accept that, you cannot stop halfway. You cannot say the vacuum energy is real enough to push two metal plates together, but let us not worry about whether it does anything else, because it should do something else, something enormous, something cosmic, which brings us to the crisis, the real crisis, the one that keeps theoretical physicists awake at 3 a.m, staring at the ceiling and wondering whether everything they know is wrong. In Einstein's general theory of relativity, all energy is a source of gravity. All energy curves space-time. A photon curves space-time. A hot cup of coffee curves space-time slightly more than a cold one. A compressed spring weighs more than a relaxed spring by a tiny, unmeasurable but done-go amount. Energy is energy, and gravity does not care where it comes from. It does not ask for credentials. It does not check whether the energy belongs to a rock or a ray of light or an empty vacuum. Energy is energy, and gravity responds. So if the vacuum has energy, if the zero-point fluctuations of all those quantum fields contribute a done-go energy density to every point in space, then that energy should gravitate. It should curve the fabric of the universe. It should affect how fast the cosmos expands or contracts. It should show up in the large-scale structure of everything we can see. So how much energy does the vacuum have? This is where the nightmare begins. When you try to calculate the total vacuum energy density, you have to add up the zero-point contributions from every quantum field at every possible frequency. And not just the electromagnetic field, every field. That electrons have a field. Quarks have fields. Neutrinos have fields. The Higgs has a field. Each one contributes its own set of zero-point oscillators, each with its own 1/2 h-bar omega. Now, we do not know physics at all scales. At some point, at extremely high energies, our theories must break down. There is a natural scale where this happens, called the Planck scale, where quantum mechanics and gravity become equally important, and neither can be ignored. The Planck energy is roughly 10 to the 19th times the mass of a proton. It is an energy so enormous that no particle accelerator we could conceivably build would reach it. It is the energy scale where space-time itself becomes fuzzy and uncertain, and the very idea of smooth space starts to dissolve. If we use the Planck energy as our cutoff, if we say we will add up zero-point contributions only from frequencies below this threshold, because above it we genuinely have no idea what we are doing, we get a number for the vacuum energy density. And the number is monstrous. The predicted vacuum energy density comes out to something like 10 to the 113 joules per cubic meter. Let me paint that for you. A 1 followed by 113 zeros. Not total energy in the whole universe, per cubic meter of empty space, of nothing. If this were the real energy density of the vacuum, the gravitational effect would be catastrophic. Space-time would be curved so violently that no atom could exist. No star could form. No galaxy could hold itself together. The universe would either fly apart in an instant or collapse into a singularity. You would not have had time to form a thought, let alone build a telescope or ask a question. Now let us compare that with what we actually observe. This requires a brief detour through the history of cosmology, but it is worth it because the story is wonderful. When Einstein first wrote down his equations of general relativity in 1915, he found something disturbing. His equations described a universe that was dynamic. It had to be either expanding or contracting. It could not just sit there, static and unchanging. But in 1917, everyone believed the universe was static. It had always been there, it would always be there, and it was not going anywhere. So Einstein, uncomfortable with his own prediction, added an extra term to his equations, a constant, a fudge factor, really. He called it the cosmological constant, and its purpose was to provide a kind of repulsive gravity that would balance the attractive gravity of matter and keep the universe from collapsing. Then, in 1929, Edwin Hubble measured the speeds and distances of dozens of galaxies and found that they were all flying away from us. The farther the galaxy, the faster it was receding. The universe was expanding. Einstein's original unfudged equations had been right all along. The universe was dynamic, it was growing. And the cosmological constant was unnecessary. Einstein reportedly called the cosmological constant his biggest blunder. He pulled it from his equations and tried to forget about it. But the cosmological constant refused to stay dead. In the 1990s, two teams of astronomers set out to measure how fast the expansion of the universe was slowing down. They expected it to be decelerating because gravity pulls things together, and over time the mutual attraction of all the matter in the cosmos should be putting the brakes on the expansion. They used distant Type 1a supernovae as cosmic distance markers. These are exploding stars that all reach roughly the same peak brightness, which means you can figure out how far away they are by measuring how dim they appear. What they found in 1998 shocked everyone. The expansion was not slowing down, it was speeding up. Something was pushing the universe apart, something that behaved exactly like Einstein's cosmological constant. A uniform energy density pervading all of space, acting as a kind of anti-gravity, gently but relentlessly driving everything away from everything else. Cosmologists call it dark energy. It makes up roughly 70% of the total energy content of the cosmos. And it looks for all the world like the energy of the vacuum. We can measure how strong this dark energy is by studying the recession of distant galaxies, the patterns in the cosmic microwave background radiation, and the distribution of galaxy clusters across billions of light years. All the measurements converge on the same answer. The observed vacuum energy density is approximately 10 to the minus 9 joules per cubic meter. 10 to the minus 9. compared to the theoretical prediction of 10 to the 113. The prediction overshoots reality by a factor of 10 to the 122, a 1 followed by 122 zeros. I want you to appreciate the scale of this error because numbers this large stop meaning anything.